All right, let's get started. So today we're going to complete the discussions on convolutional neural networks by talking about what you can use for convolutional neural network for dense prediction problems in computer visions. All right, so and also just a reminder that that this will be the cutoff. Like after this lecture, everything we talk about on Tuesday will not be on exam. But today is the last part that you could be on exam. Okay. All right. So as a continuing our discussion on convolutional neural networks, basically the key insight is that you take a linear layer. Basically, you have input, and then you connect everything in the hidden layers using linear connections. And if you take that linear layer and you assume two things like local connectivity and weight sharing, and this will gives you the concept of convolution operations. Okay, and so the idea, and then you can further extend that to handle multiple input and multiple outputs, right? So here the connectivity. Basically, you have a filter that is being applied to all the positions. So that filter only has C inputs within a local regions. And if you weight sharing, basically means that all the location is being used. You can compute the entire feature response by applying the same feature weights on different locations. So that is weight sharing, share across different spatial locations. And you can handle multiple inputs, like a different input channel, maybe it's RGB, and then this could be multiple different filters, and you can generate multiple different filters. So this is one convolution layer, one more convolution layer is doing. Okay? So here, what you can see is that different activations match what it would become like a different tensor here. Each of them, they have its own particular filter. So you could imagine that if I want to detect a particular features, one features this feature may be detecting horizontal edges, that feature may be detecting vertical edges, another feature could be detecting oriented edges, okay? Or another feature could be detecting a particular corner, right? So in the earlier layer, you extract some kind of these low-level features, and then gradually at the next layer, what you will do is that you will again compute some kind of combination of these local features. So that's why you get something that's more and more abstract and more semantics. Okay, but the interesting thing is that you don't need a human to tell the model, say, okay, I need to detect these vertical edges first, and gradually, you don't need to tell them how to combine these progressively more meaningful features. You just give them the architectures and then learn from the data. Okay, so this is good. And since then, people take this idea, and there have been a lot of advances over the years. I'm going to do a speed run on how these ideas come to life. Okay, so in the 80s, people, like you can see that this is 80. They look at this same ideas. Basically, you have from input images, and then you gradually kind of compute features and aggregate features from lower resolution to a higher to a lower level feature to gradually higher level features. And at the end, you can make predictions. All right, so this has probably get some attentions when we are in around 1993. Okay, so this is the first, probably one of the first architecture that can do. Let me just make it larger. This is the Yan LeCun when he is young. So this is what they can do. Basically, like, by the way, this is 1993. It's a very old computer, but at that time, it can do real-time digit recognitions. So they look at this digit, and then basically you use convolutional neural networks to train, and then to recognize the digits in the images. Okay, so you can see that even though the middle one is 6, even though it's handwritten, it's handwritten, it's not, or even have some bubble letter. So those models are trained to be invariant to these variations. So this is pretty cool. So this is one of the earlier success of CNN. Okay. So today, if you write a letter, you send a letter through post email, your address is going to be read by a CNN. That's turned the address actually into the actual address. Okay, so now it's kind of wrong at scale, like it's very robust. And sometimes if you think about if you receive a check or you send a check, other people can take the check and take an image, and then they can deposit their check. And the reason why they can do that is that they can recognize the handwritten digits. Okay, so this is a pretty good success at that time. All right. So convolution looks like this. You give it the input. You can imagine you have a filter, and this filter is learned, right? So you get this filter is essentially looking at similar to the CAT kind of filter we found in 1950, that it is responsible for oriented edges. And what you do is that you scan through the image, and to get for every location, you compute the weighted average of the response. Then you get some feature maps. Okay, so this is one feature map, and then you also have another set of features, and you go scan through these things, so you get another response. So you basically typically you may have maybe 64 of these kind of features or more. Then you get 64 feature maps. Okay. So these are the kind of convolution layer. But in order to construct a CNN, basically you need a couple of more, right? So the first one is the convolution layer. That's what we talked about so far. But you need to add some nonlinearity. And the most popular one, the most simple to implement one is probably ReLU, right? So this introduce a nonlinearity, basically says that if the map is negative, then you set them 0. If it's positive, then you let it pass. Okay. So it's very useful and very effective. It's very cheap to implement as well. You just check the input is for every feature dimension. If you check if it's a positive, then if it's negative, then you threshold it. Okay. All right. So in convolution neural networks, it did because it's very expensive to just process every pixels, because the image may be high resolution, and so a common approach is to reduce the size of resolutions after you process one layer. Okay, so this is called spatial pooling. The basic idea is that if you kind of you can take these these regions, and you only compute the maximum of that regions. Okay, maximum of that regions, then you get something that's smaller resolution. Okay, so this has some property that is the images, even though if you shift the image a little bit, it will still, the response will still be the same, because a local region, if you take the max, the max value will not change even if your input is slightly shifted. Okay, so and then sometimes people you can do normalization as well. We can normalize this to get higher contrast. Right. So and this is basically one layer, right? You can see, but when people talk about one convolution layer, typically usually refers to you have a convolution layers and with nonlinearity and with pooling and so on, and that becomes another feature maps to the next layer. So every time we show these guys, it's a stack of these computation. All right. And so this has been very successful. People, as I said, in 2012, people found it's very, very effective. This is when the kind of reignite the people's interest in convolutional neural networks. But if you compare this to the 1998, that the video I showed earlier, it doesn't really change too much, right? So the architecture is still basically, the working principle is still the same. The only thing is that we now have more GPUs and we train on a lot of more data. Okay, so algorithm-wise, there's not much kind of improvement. Maybe just use the rectified linear aggregation, and during training we have some dropout. Like that's architecture improvements, algorithm-wise improvement. Okay, so what does it look like? So basically, it's very similar to basically the scale of the data, scale of the compute. But at that time, it's not actually easy, right? In order to scale up the compute, you need GPUs. And at that time, people don't use GPUs. They use GPU mostly for gaming. So in order to kind of fool the GPU so that they can do science computing, that is still not easy. But people figured out how to do that, and then NVIDIA find out, oh, it's actually working. So they then go all in to support this this computation with CUDA, and that's why right now NVIDIA is now an AI company, is no longer a gaming company. All right. So what does that look like if you want to train, do the classifications? So what it does is that because it's fixed, it takes the fixed size input. So what you do is that you will, if I want to classify an image, and then what I will do is that I will randomly crop these images, and every time a crop image, you will go through the CNN and extract some feature dimension that is 4,000 dimension, and you do the corner crop, and as well as flip the image and then do another 5 crops. So in total, you get 10 estimates of this image. Then you do kind of average the features, and then you do the softmax and predict this is a certain class. Okay. All right. So what happened after 2012? So at that time, people find, it's after 2012, it becomes very successful. And then after that, people find, okay, so let's try to improve that. Okay, so take this working recipe and try to improve this. So over time, people are trying to find better and better methods to train convolutional neural networks. So I found this meme, like I was winning ImageNet until a deeper model came along. And a lot of time, it's basically just kind of find a way that can scale up the training, scale up the model. So this is kind of a joke for traditional machine learning people. Traditional machine learning people need to do like serious work, and deep learning people just stack more layers. So it's ironic, but it's true that a lot of time it's all amounts to how do you kind of actually scale things up. Okay, so it's kind of like a beta lessons for a lot of people that even though you have some clever ideas, sometimes what actually works is the data and some engineering that make things scale up. Okay, but to get there, you usually need some kind of architectural changes to actually make it work. Just to name a few, you don't need to kind of these probably, if you go interview at some companies who do computer vision, this will probably come up. But I don't think you need to remember these like hardcore this knowledge in your brain. Just like people have been improving these architectures, and maybe you want to understand what the principle behind those architectural improvements. So and then I want to summarize each work, like landmark papers along the way, and there's their core message there, right? So the first one is probably VGGNet. It's highly influential. The basic idea is that at that time, the AlexNet was just maybe a 5-layer neural network. What they said is that you can scale this up by making things deeper, okay? So the deeper, the better. That's the basic idea of this model. And how to make things deeper, the way you make things deeper is that you use a smaller convolutional kernels. So AlexNet is still use like 11 by 11 convolutional kernels. And in this case, starting there, they start to use very small convolutional kernels. And this kind of idea has been propagated throughout the rest of the papers as well. Okay, so why you can use smaller kernels? It's the following. If you have a convolution, if you have a filter like this, if like a 3x3 filter, if you only have one layer, then every output only see a 3x3 window of the input. But if you have multiple layers, even if you only have 3x3 layers, 3x3 filter for every layer, your receptive field will still grow with this, like the second layer will see the filter output from the first layer. So effectively, the second layer will actually see a 5x5 window of the input. Okay, so get something that's larger. Okay. All right. So the message in this paper is that if you reduce the size of the filter, you can improve the model performance. But the problem is that later on people find that can we just increase the number of layers just naively? But what they found is the following. So if you what they found is that if you take the 20-layer model, this is training loss and validation loss. And what they found is that if naively stacking more layers doesn't really help. Okay, like in this case, it doesn't really help to improve the training error and the validation error. So it seems that it's weird, right? Because we know that deeper models should perform better, but the problem is that they show that it doesn't. And why is that? And even a training loss, it doesn't really improve better. It doesn't perform better. The main problem is that it's not because the model is not sufficiently expressive or have more capacity. It's because that it's more difficult to train on this model. And what they found is that, again, a very simple idea, you just add residuals. So instead of having just directly train the model so that you stack the model together, what they found is that every layer you have a residual, you only learn what you should change about the inputs. All right, so you have the inputs, and you only change these layers with these convolution layers. Only in between. You only change these things. So this is called residual connections. Super simple idea, but you probably can find this design in everywhere, every neural network, every ChatGPT or every Gemini. This must be there. Okay, so the key idea is the following. So you have this model. This becomes your layer, and imagine you stack multiple layers like this. And if you have a training signal at the end, you have a kind of loss. And what happens is that you will take the loss in your computer gradients and try to backpropagate the gradients, right? If you have this design, if you have gradients from here to go up and try to backpropagate this one, right? The idea is that because you have addition here, so the gradient will actually distribute it, right? Remember that? Like it's a chain rule of backpropagation. So the gradient will go up here and also go here. So which means that your gradient will not be attenuated by these layers. So this provides a clean signal for training a very deep neural networks. So even so sometimes earlier before, if you don't have these residual connections, what people found is that if you train on deeper model, you will get something called vanishing gradient problems, because every time you need to kind of backpropagate through this convolutional layers, and it is harder to train the earlier layers. Okay, that's very far from the loss function. But with this residual connection, you are able to kind of reuse the gradients from the loss term. All right, so it's very useful. Okay, you will see every design has this. Okay, so residual connection works. Why not just because but it's only connecting one layer to the next layer. Why not connect to all layers? And so people also experiment that. So you can see that at that time it's both mostly these kind of very simple intuitive ideas, but it has a huge impact. So what they did is that, okay, you just apply residual connections to all the layers, and that's basically it. And it's called DenseNet. And yeah, so and recently there's also some variants that in the context of transformer, that also the people also revisit similar ideas here. Okay, so people have been experimenting with variety of different kind of model to train convolutional networks, and you need the general thought is that you need some kind of like tricks to actually train it well. Okay, so the basis is that you have this backpropagations and stochastic gradient descent. Okay, and later on we'll talk a little bit about how you can train the regularize the model with some other techniques like dropout, data computations, normalization, and so on. Okay, so quick recap. Basically, you have a model that is parameterized by W, a bunch of like learnable weights. Like the rates is essentially the filters. Like you initialize with random, you don't know what the weight should be, but you specify the functionality of that. So you have a f, so you have a score function, and then you create you have a loss. Then every time you can compute the loss, and you can take the gradients with that. So this part, you take once you be able to take compute a loss and take a gradients. This part is coming from the backpropagation, right? You have a loss, and you can backpropagate the gradients, compute the gradient of the loss with respect to every parameters. Okay. Once you have that, you can update this toward the negative directions of the gradients, and that's how you can do the gradient descent. Basically, that's that. Question so far. This is just a review of how you will train any neural network, like a CNN. Okay, so I think this part we already talked about before. That is when you have a computational graph, how you actually train it. For example, if you have the key idea is the backpropagation that use a trend rule. So the key idea is that if you have a combined computations, you have a x plus y times z equal to qz, then you know how each computations, what's the gradient between the input and output. This is each computation. This is x plus y. You have the local gradients, and here you have local gradients. And then once you have that, you can take the output gradients and then gradually propagate, like kind of go back and then see what the gradients of the loss with respect to each of the inputs. Okay, so this is how you can find the gradients for all the parameters. Okay, so basically that's the idea. Very straightforward. Questions so far? Okay. Okay, so once you have gradient, then there are many different training tricks. I don't think I will want to talk in too much detail on all this, because this probably you will probably encounter that in many other machine learning related classes. But I just want to kind of go a rundown to show you that there are many different kind of training techniques people come up with over the years to improve the performance. Okay, so one of the most important one is probably called dropout. Okay, and the main idea is very simple. Like instead of imagine that you have some linear layers here, you want to train this model. Instead of relying on everything active at the same time, they just say that okay, during training, randomly with some probability you will remove part of the node. Okay, so basically you are training the model. Make sure that every time if I mask out maybe 50% of the neuron, I will still be able to correctly predict the model, the results. All right. So one way to kind of to understand intuitively why this will work is the following. So imagine that you want to conspire something bad. Okay, so then you have two strategies. You have 50 people to conspire, planning that conspiracy, and you have strategy A, that is every 50 people, like all the people are neuron, to plan jointly. Okay, it's probably likely will fail, right? Because 50 people need to every person need to be in sync, right? Every people play a small part. Okay, it's hard to make every people coordinate correctly. And the strategy B is to plan 10 conspiracy, like 10 pranks or bad things. Each one of them involve only 5 people. Okay, so it's much more higher chance to succeed because you only need 5 people to make it work. Okay, so yeah, so this is a very effective method, very simple but very effective to train this model. And it's being used everywhere, like as well. Like any neural network training, you probably will have dropout inside. Okay. All right. And another one is the jittering. Basically, whenever you have the data, because the model data is really important, the diversity of data is very important for the model to generalize to unseen cases. So, but you only have finite set of training data. So a typical way to improve the model performance is to make sure that your data, you can augment the data so that you have as if they are new data. Okay, so a common way to take an image is that you do random cropping to do jittering, and noise, blur, and so on. So these are the common way to increase the number of data, even you don't have that many. Okay, and this has been, if you work on anything, this has been kind of standard practice for you to improve the data, improve the model. Okay. Activation, people also look at how you can further improve the activations. For example, ReLU is the baseline, and people can find maybe you can, instead of using the flat lines, and you can use a parametric way to improve. There are also many different other choices, like a swish and so on. Like people design over the years, people have been designing different curves and nonlinear curves that see which one works better. Okay, so there are kind of long list of options, but when in doubt, you probably should just use the simplest one to start with, and then you can find kind of better versions there. Okay, all right. So, question about CNN. In following, I'm to move on to talk about the computer vision tasks. Okay. All right. Stop me if there's anything that's that yeah, if you have any questions. All right, so far we basically we describe a standard architecture that can do classification, right? Basically, you have something and then you can make predictions at the end. But a lot of problems it does not like that, right? So for example, if given an image of a cat, you may want to do semantic segmentations, right? So you want to basically label every pixel what the semantic class of that pixel is. So for example, this is very important. Let's say you are building a self-driving car model or robot, or you need to know where you can go, right? So labeling pixel that is raw, drivable or not drivable, that's very important problem. Or you want to have a robot, you want to recognize object that you can manipulate, recognize the chair that you can sit, and so on. That's very important. Okay, so semantic segmentation, basically segment every pixel into a semantic class. Another problems are kind of if you have multiple objects, it's not just about segmenting out pixels, right? So what you want is really to group up. Okay, this instead of saying that all these two are dogs, you want to say, okay, these are the one dog and these are not a dog, right? So be able to detect objects. That's also a core problems in computer vision. And the instance segmentation is kind of like a combination of these two. Like you not only want to detect, but also within a box of detected object, you also want to segment out the objects. Okay, so it's increasingly more increasing granularity of the problem. Okay, so let's talk about how you can adapt the classification model that's coming from CNN to tackle these problems. Okay. All right, semantic segmentation. So as I said, it's basically the problem setup is I give you an image. For every pixel, you give me a label, and each pixel is maybe it's a 100 class or 20 class. You have a predefined object categories, okay, and you want to predict these classes. All right, so how do we do this? The simplest approach is the probably the following, right? So I take this image. I already have a model that takes a fixed size patch and predict a class. The simplest model is take this image, and for every window, I pass through this model, CNN model, and predict the class label. Okay, what's the problem of this? It will work, right? So if it basically, yeah. Yes, it will be very, very slow. It will take, basically the idea is that you will need, because there are many, many windows in the image, right? So you will need to scan you need to run through the model many, many times to get that results. So this is very inefficient. So what should we do in this case? So maybe what you can do is that let's build a convolutional networks. Use convolutional networks, but instead of trying to make predictions early on, what you can do is that you can just take the image and then build a convolutional networks. You have these filters. You have these filters, and in the end, you can make a prediction of the scores. And then you take a softmax. You pick the one with the highest score, then you get a prediction on the right hand side. Okay, so you extract the features all at the same time. So this is better, but can you imagine what could be the problem here if I just use this? What could be the problem of this is Any idea? So now I'm able to share the computation across different pixels, right? Because I have convolutions. But now, in order to remember that our filter is usually a small filter, right? That the kernel width, the kernel size is small, like a 3 by 3 or 5 by 5. And when but here the cow is very large, right? So in order to recognize that pixel is a cow, we need to see a large regions in the image to say that as a cow, okay? So in this case, we don't have that, right? We are not able to, we need many convolutions to actually capture the whole picture of the image, okay? So it's still, especially this is very expensive, especially when you have a high resolution image, right? The cow is very large in the image. Okay, so probably a more so what people can do is that, okay, so you take this idea, but instead of using this, and instead of only using this, you add a downsample operations, okay? But at the same time, you want the output to be the full resolution, because the task is about every pixel location you want to assign a class. So in addition to downsampling, you also added upsampling operations, okay? So when you do the downsampling, you can reduce the size. So now, if any filter that's just 3 by 3 in the downsample versions, it's effectively much larger in the original input, okay? So you have in the lower resolution, even though you have a lower resolution, a small filter in the lower resolution is going to be a large, has large receptive field at the high resolution. So this is the same concept when we talk about Lucas-Canade, right? Lucas-Canade has this concept that if I want to track small motion, I need to downsample the image so that I can track the small motion in the low resolution image and then gradually propagate the solution upward. Okay, similar concept. Okay. So for downsampling, we can do the pooling and strike convolutions. This is very easy. But how about upsampling? There are actually many different approaches. Maybe you can do, like if you have a 2 by 2 kernel response, like 1, 2, 3, 4, and then you can do the upsampling like this. You can do the bed of nails, like basically move only the 1, 2, 3, 4 the top left corner, or you can do the, like when you do have the corresponding layers. When you find the max pooling, you just move the max one to the correct locations. Okay, so all these are valid options. People have been trying different ones. Probably the most popular one is called this 1D. Probably the popular one is called the transpose convolution. Basically, the idea is that you also learned what you also have a learnable parameters to do upsampling. Okay, so the concept is very simple. Like given this input A and B, these A and B, I want to generate like a higher resolution output. And the way I do this is that I have an X, Y, Z. Then I take the A is a single number. I take the filter, you get an X, Y, A, X, A, Y, A, Z. And then you take a B, and then you get a B, X, B, Y, B, Z. So now you have a higher resolution, right? So yeah, so you can do this. Then you get the input that's smaller resolution, and output it becomes higher resolution. Okay. And this is also called a transpose convolution. And the reason why it's called transpose convolution is that you can express the convolution as a matrix vector multiplications. So imagine that you have a filter like this, it becomes this is actually doing a convolution. and the filters looks like, the matrix looks like this. The filter is just XYZ. And the transpose convolution, it comes from with that name because that is literally the transpose of this matrix. Okay, so you can see that if now I have A, B, C, D as input, it's shorter, and then you can increase the resolution by adding these using this matrix. Okay. All right, so once you have that, basically the multiple different methods, then this is basically the canonical way of solving the semantic segmentation. Okay, right. So input, and then you have a CNN model, but you use a fully convolutional model, so that kind of extract the feature first, and then do the classification, not doing the classification at patch level. And you have the downsampling and upsampling operations. That's basically it. Okay, questions about this? All right, so how do we do the detections? So now we can label every pixel as a semantic class, but now what we need to do is to detect objects. Okay, so here's just a plot to show you the progress over the years. On the before the deep networks come in, so this is, you can see that this is before 2012. People are like every year they're trying to design better algorithms, and they kind of plateaued, right? So you can see that they improving and then gradually kind of saturated, the performance saturated. And after 2012, you have a big jump, and then people get improved over time. Okay. All right. So how you could solve this, right? So maybe the simplest one is the following. So you have an image, you run through the CNN, and you can take the CNN and then solve for predicting not just the object class, but also where the object is, right? So maybe you can predict the bounding box coordinate, right? Predicting where the object is. And because you have training data with the ground truth, so you could train this with certain laws, with softmax to predict the class, and use the correct coordinate to predict the bounding box. Okay, and you add them all together, you get a final loss. So during the training, what you'll do is that you will take this loss, you will backpropagate this gradients to train this model. So you can this is how you can adapt the classification model to solve detection problems. Okay, so usually you will pre-train this on some large scale image classification problems, and then you adapt this to this problem. Okay, so can anyone tell me what's the problem of this? How can we, like, what's the problem of this combination if I want to do the general object detection? Any idea? Okay, so how about this? What's the problem of this? If I use the same methods. Any thoughts? No problem with this? What could went wrong with this? Any idea? Okay, so the main problem is that we we sort of need to know how many numbers of objects are there, right? But in practice, we don't know, right? In this case, for example, if we want to train this model, we need to know, okay, there are one object, then I need to predict 4 numbers. If there are 3 objects, I need to predict these many numbers, and so on. And what if we have many different objects? Then I need to predict these numbers. But the problem is that I don't know how many objects are there, right? So this could be the problem. If you directly predict, given a box, and you want to predict where the coordinates, where the object is within this box, that itself assume that you only have one object inside, okay? So you can do localization, but you cannot do detection. Detection means that you don't know how many of them. Maybe they are 0, maybe they are 100. So this is the challenging problem, okay? So maybe one way to do this is to reframe the problem as a classification problem. So the idea is that if I try to say, okay, is this a dog? No, it's a background. Yes. And you can say, okay, this is definitely the dog, and this is the dog. And is this a dog? No, it's a cat. Okay. So if you can pose the problem as that you have some hypothesis saying that which regions are the a potential object, and you use the computer, use the CNN model to do the classifier, then you can do the job. Okay. So here's the problem is that you have so many different bounding boxes inside the image. So you couldn't really try out all the possible bounding boxes in the image. Okay. So fortunately, at that time, computer vision people have some methods that can kind of provide maybe 1,000 or 2,000 bounding boxes that has potential that's potential candidates for an object. Okay, so there are some off-the-shelf methods that can do this. All right. So how will you a method works like this? Okay. So the main idea is that given an image, you have some candidate boxes, like maybe 2,000 of them. Okay, you have 2,000 of the boxes. Then what you do is that you extract the CNN, take these boxes, resize them to fixed size, pass through CNN, and then do the classification. And then you can, once you have that, you can regress where the bounding box is, because every box now has only one object inside. Okay. Okay, so you can do the bounding box regression to predict where the box actually is. Okay, so what's the problem of this approach? This definitely works, right? But there's some problem with this. The thing is that it's still very slow, right? You need to have, let's say, 2,000, right? So there are 2,000 bounding boxes candidate. So you still need to run this model 2,000 times. Okay. So it's similar. You see that it's a similar challenges when we talk about the semantic segmentations. So what we'll do here is that, okay, so instead of having all these bounding boxes, maybe we can process, instead of processing each bounding box independently, let's just process them before the cropping. So just swap, like you can see that they crop the image and resize, and then do the processing. So maybe you can directly process the image with the CNN directly. Okay, so you can extract the features instead of having to extract features for different regions. Okay, so this is a kind of, this CNN is slow, so it's called slow RCNN, region-based CNN. And what you could do is to have a fast CNN. By the way, this is the actual paper name that you just say fast on CNN. What they do is that you swap the role of cropping images and CNN. You first extract CNN, and then on top of that, you extract features, right? So instead of before you first crop the image and then you resize the image and then extract features. You first then you change that with extract the features and you crop the features. Okay, just very simple changes, and then you can make the predictions. Okay. All right. And then with this, you can actually like this is just show you how you can get the feature, extract the features. For example, if you take the image and extract some features, and the bounding box essentially looks like this, right? So one way to extract the features is to snap the bounding box, snap to the closest bounding box, closest feature grid, and snap to grid. Right? And you can extract features like this. To max pooling, you can extract features like this. Okay. The problem is that the features do not entirely align with, because the CNN has features that not align with the image. So you will have some misalignment. So a better approach is to do alignment, right? So basically, you extract features along the regions and you do the interpolation to get the better features. So this is the same interpolation you did when you do the Lucas-Canade to try to get subpixel accuracy. Okay? You get interpolations, bilinear interpolations to get a better features. Okay, so basically now you have this, right? You have an RCNN, fast RCNN, and so on. So, so here's the kind of speed what you see. Like earlier in RCNN approach, basically you crop every bounding boxes and you pass to the CNN to do the classifications. What happens there is that your main computation overhead is mostly on processing the CNN features. Okay, so this 47 seconds, and once you do fast RCNN, what happened here is that now the CNN features extraction is very fast. It's like a 0.32 seconds. But now the region proposal, that basically the external algorithm that gives you the bounding box proposals, they takes 2 seconds, like more than 10 times, around like 8-9 times than the actual CNN itself. So here's the problem, right? The proposal itself takes a lot of time. So what should we do in this case? The CNN models can extract feature very fast, and once you get a bounding box, you can do the classification very fast right now. But the problem is that the bounding box itself, to generating the bounding box itself is slow. Any ideas how you can address this? Okay. Any thoughts? How you will address this? So now with the dilemma we have is that now we swap the feature, right? We swap the feature cropping, image cropping with feature cropping. Okay. So we can extract features very fast. But in order to crop the features, I need to run another off-the-shelf method to give me the bounding boxes. So how can we improve this further? How can we make this faster? Any ideas? Just any thoughts is welcome. Anyone? I think this is important because if you read all these literatures, you'll find that kind of if I directly tell it to you, it's feel natural, but the problem is that you won't remember anything if you don't try to put yourself in the shoes of these advances. I feel that the learning will be limited if you just like know what people have done. I think it's important to see, okay, what the dilemma people have tried, have encountered, and then think about yourself. Okay, so I want to get some ideas from you, even though it may not be the best, may not be the right way to solve it, it's fine. How you will solve this problem right now? Okay, so let me try to understand, give you a more context. Okay. So previously, it's on the right-hand side. That's the first version of the computer vision model for doing detections. Basically, we take images and then we crop images, and then for each regions we do the CNN classifications, right? So this is slow because you need like 2,000 times of evaluations of CNN. So this is bad. So instead, what we could do is that we take this image and then we extract features first, and then do the cropping of the features, right? Instead of cropping the images, we crop the features because now you share all the CNN computation into from 2000 to 1, right? So now you get much faster feature extractions because you only extract feature once. And then you only need to do the cropping and then do the classification for each regions. But now the question is, the problem is, now the dilemma is that these bounding boxes are coming from other models, other kind of off-the-shelf methods. Those methods are not easily accelerated. So if you were the researchers at that time, how will you address this? Like we talk about this, like this process, if you remove the region proposal, it only takes like 0.3 seconds. But now the region proposal becomes the bottleneck. Yes. Oh, exactly. Yeah. So if you come up with this, that you won the test of time award last year. This gets like basically you are the famous researcher right now. Like if you are the so that's very, very simple, right? So you see that you can easily you can come up with these intuitive ideas. So on the right hand side, you have a slow kind of RCNN, fast RCNN, and people call it faster RCNN. Okay, so that's kind of how they name these things. Yeah, so basically the same thing. You just ask the model to predict the region proposal, right? So so you can see from this figure, they take an image, you have to track CNN, then you have region proposed, and then you have a use a model to propose its bounding boxes. You can train this one and then use this bounding boxes to predict. So everything become end to end. Okay, so this is the key that you can make things end to end trainable. Let me just try to see if I can find how this simple idea that you just come up with. Okay, so if you look at maybe just to see what the Google Scholar looks like. So this is fast RCN, you get like a 45,000 citation and this faster, then that's the idea. Then you get you could have 50,000 citations. That's probably more than kind of probably every faculty in the department. All right, so it's very influential, and you can see that it's very, very simple. All right. Okay, so how does kind of the idea, but how do they execute that? Okay, so the basic idea is very simple. You have image features, and then what you do is that for every image features, you have this anchor and then predict where basically the same ideas of bounding box regressions. For every you have anchor, you predict what the feature transformations should be so that you can regress the bounding box. Okay. Right. So yeah, so there's some details, but that doesn't matter. So once you have this, you can reduce the speed, right? So you can reduce the speed from RCNN to a faster RCN to faster RCN. So you get a 0.2 seconds and to run inference. It becomes much, much faster. Okay. All right. But the thing is that people find that, okay, later on people find out why do we need to run the first stage, right? Why do we need to find the bounding box first and then do the classification on each bounding box? So what people find is that maybe I can just take the image, extract features, and directly just one single stage, right? So I can do the following. For every bounding box, every features, given the image, I have a feature extractions, and then you have every location that's a feature. You just use some candidate anchors and directly predict what the box is and object class is. So this gives you the concept of you only look once. That's YOLO. So if you are interested in more real-time object detection applications, then these are probably the go-to solutions you'll use. Okay, you basically train the model that don't need to look at the bounding box first and then do the classification. You directly predict what the bounding box and the classes of those boxes. Okay, so you can design these type of methods. Okay. And I don't know how many versions are there. Like the version is very bad. Like sometimes YOLO 7 is come out earlier than YOLO 6 because people just do there's no single person or organizations publishing that same version. So people keep running around different numbers. Okay, but the concept is the same, right? Basically, they have the single stage networks. Okay, so these are, and then once we have this, what will happen? Now you have the detections, and at the same time you have segmentations. Then it becomes intuitive to combine them, and the way to do this is called mass RCNN. Okay, so the key idea is very simple. Like you have the CNN features. With faster RCNN based on faster RCNN, then you align these features. Now you get the features. You just treat these features as semantic segmentations. So you predict the segmentation mask within these features. Okay, so you are able to do this kind of detect the bounding boxes and be able to segment out the things, segment out this band, this person, and so on. So this becomes hugely successful around the time, and even today, if you want to do any kind of semantic segmentations, this is probably the go-to methods that you can use. Like if you're given an image, now you are able to detect arbitrary objects and segment out objects very reliably. So here are some examples, and you can also extend this to poses as well. So given the image, you actually can detect persons, segment out persons, and be able to do the annotate the pose of the persons. Okay. Right, lots of tools online, so you can take a look. If you want to use for projects, that these are also interesting building blocks for you to use. You can use this to detect any objects you have in mind. Maybe the hand gesture, then you can use this to control computer, or you want to do this for traffic analysis. You want to use this for kind of self-analysis or any type of applications. So this has been kind of the core computer vision building blocks. Okay. Let me see. Okay, I think I'll skip the rest about kind of going beyond 2D detections. I'll revisit those after we talk about more like transformer-based architectures. Okay. All right. So next Tuesday we will be talking about transformer. That is, if I said that convolutional networks dominate the 2020 since 2012 and up to 2020, and transformer probably is the one who dominates the 2020 this decade. Okay, so most advanced model are based on transformer. Every large language model that you use are based on transformers. So I think that will be an important thing to learn if you are interested in anything related to AI. Okay, and then remember that next Thursday we'll have exam. Okay, thanks.